Let's take a look at how to solve the third FRQ from the AP Chem exam. So this whole FRQ looks like it's mostly going to be acid bases and some equilibria with a titration. And then we have some indicator stuff going on here at the end. So for part A, they want us to identify the conjugate base pairs of the substances that we have in equation number 1. They give us the respective K value and the temperature, and they want us to clearly label which is the acid and which is the base. So already looking at our equation here on the reactant side, the HNO2 is going to be our acid, and then the H2O is going to act as a base. So then the respective pairs are going to be for the HNO2, its pair is going to be the NO2 minus, which is the conjugate base, and then for our H2O, which is going to be a base, its conjugate pair is going to be the H3O plus, which is going to act as a conjugate acid. For part B, we have 2 individual questions here. For the first one, it says calculate the value of the H3O plus in the solution if we have a molarity of 0.125 and the final pH is going to be 2.09. So we know that to calculate pH, it's equal to the negative log of the concentration of H3O plus. So we undo that, and we now have the molarity of H3O plus is going to be equal to 10 to the negative pH. And so we have the pH value given to us, so we just plug that into our expression here. So our molarity of H3O plus is equal to 10 to the negative 2.09. So then we solve for that, and then we end up getting 8.1 times 10 to the negative 3 molar, and that is our molarity. So that is our answer for the first question here for part B. So for the second part here, they want us to solve for the HNO2 molarity at equilibrium. So we have to set up our K expression and look at our relationships at equilibrium. So we have the NO2 minus multiplied by the H3O plus, then divided by the HNO2. So we reuse our answer from the last question where we calculated the H3O plus concentration. And then we know that for every 1 mole of the H3O plus, we should have 1 mole of the NO2 minus. So then our K value, which is given to us already, is then going to be 5.6 times 10 to the negative 4 is equal to the 8.1 times 10 to the negative 3. And then that's going to be squared. We then are dividing by our unknown, which is the original acid, which is what we're solving for. So then we rearrange this. And then once we simplify, we get 1.17 times 10 to the negative 1. And then based on the K value, we should have way more reactants compared to products. And if we compare these exponents here, we have negative 1 compared to negative 3. And then so based on our given ratio, this helps us verify that this is a weak acid. For part C, there's another set of 2 questions. And there's an experiment where the solution is 0.125 molar of the same acid, but it's heated now to 333 Kelvin. Compared to before, our temperature was at 298 Kelvin. They give us new equilibrium concentrations, and then those are provided below. The first question says, calculate the value of the Ka of our weak acid at the new temperature. So we know that K is only dependent on temperature, so if that changes, we have a new ratio between our products and reactants. So our expression is still the same, where it's products over reactants, but now we just plug in all of these respective values. So then we have the 0.0109 molar, and then we could just square this because it's the same concentration for both of these products, and then we divide it by the concentration of our reactant, which is then going to be this, and then we're able to simplify. So then we get 1.0 times 10 to the negative 3. So that is our new K value compared to our K value before, which was to the negative 4th power. So K increased as temperature increased, which then leads us to our second question here, where they're saying, is the equation number 1 endothermic or exothermic? And they want us to justify based on our new K value at the higher temperature. So Because K increased, that means that we proceeded now in the forward direction because we increased the amount of products that we have. And so if the temperature increases and we favor the forward direction, this is consistent with an endothermic reaction. So we would then say that this is endothermic because Ka increased at a higher temperature. The forward reaction is favored. This is consistent with endothermic. That means that as temperature increased, we had to bring temperature back down. And then so the only way to bring temperature back down is to consume heat as a reactant, which is then consistent with our endothermic prediction. A second experiment is conducted where a student uses the same acid, but now the molarity is unknown, and they want to do a titration in order to determine this unknown concentration. The volume that they use to titrate the weak acid is 35 milliliters. And then they use a strong base with a concentration of 0.16 molar at 298 Kelvin. And then they give us the equation for that reaction that happens from the titration. Part D, they want us to use the graph, figure 1, to identify the pH at the equivalence point. So we have this range here, and then we want to see, well, what is most medial? And it looks like this is going to be our pH at the equivalence, so that our pH is going to be equal to 8. They just want us to identify, no justification needed, pH is equal to 8. One of my students said that they put a pH of 7. I would say that's a little bit too low. I would also assume that a pH of 9 is a little bit too high. It ideally should be close to 8. For part E, we want to use the same graph in order to calculate the molarity of the HNO2, which is the whole goal of this titration. So in order to calculate the molarity, we can use the expression M1V1 is equal to M2V2. And if we look here, it's a 1-to-1 ratio between our acid and our base. So because the number of moles is equivalent, we can use this expression here. So then we're just going to use the left side as the acid, so we don't know the molarity, but we know that it had a volume of 35 milliliters. And then the base had a known concentration of 0.16 molar. And then based on our graph, we can see it required 50 milliliters to reach the equivalence point. So at 50 milliliters is when we had equal moles of the acid and the base. So then we solve for the molarity. The molarity is then equal to 0.23 molar. So that is the molarity of our weak acid in this bottle that was handed to the student. Part F wants us to draw an X on our graph to represent the point in the titration where the concentration of the weak acid is greater than that of its conjugate base. And then so at the half equivalence point, those concentrations are equal to each other. So then if it required 50 milliliters to reach equivalence, it then required 25 milliliters to reach the half equivalence point. So at this point in our titration curve is when they're equal to each other. So then we have to think, well, on what side do we have a greater amount of the original acid, the weak acid? And that's going to be somewhere here. So I would say as long as your X is between 0 and 25 milliliters on the X axis, you're probably going to get credit for part F here. Part G then tells us that the equilibrium constants for these different reactions are given in the table below. They give us the Kw at 298 Kelvin, and then they give us the Ka of our weak acid, and then they give us this K2 value, or at least we're going to solve for the K2 value here for this part. So then we have to do our mechanistic magic here, where we have to cancel our intermediates in order to get these first two equations to reflect the equation that's happening here for K2. So we take a look. The HNO2 is on the same side with the same coefficient, so we don't have to do anything to that K value yet. We take a look, and the NO2 minus is on the same side with the correct coefficient. And that's really only the things that match from our K2 reaction, and then the first reaction with the Ka. So then we have to go to the Kw expression, and then we want to be able to identify the OH minus. So the OH minus shows up as a product here, but it needs to be a reactant. So that means that we have to flip this Kw expression, but instead of just flipping it, we take the reciprocal. So then we have the reciprocal of the Kw. Once we flip that, we end up with the OH minus on the correct side, and then we also end up with the H2O on the correct side. We get 2 moles of H2O on the product side for the Kw, but one of those moles will cancel out from the Ka value that we have up top. So then that is then good to go. So they want us to calculate K2. So K2 is then going to be equal to our Ka, which we didn't have to do anything to in order to get that equation to match the bottom one, multiplied by the reciprocal of the Kw expression. So then we plug in our numbers. So then we have 5.6 times 10 to the negative 4 by the reciprocal of 1 over 1 times 10 to the negative 14. Our K2 value is then going to be 5.6 times 10 to the 10th power. And if you take a look, there's this really small detail that they didn't include, or at least we might have overlooked it. This reaction is not equilibrium. It only proceeds in the forward direction, which is consistent with something that goes to completion. And based on the K value that we just calculated, this reaction very much favors the products, which would tell us that it really is only going to go in the forward direction. Our last part here for this FRQ is going to be part H, where we have a data table with these different indicators and then the pH at which they change color. A student conducts a second titration, and they add 2 drops of the methyl orange indicator to our 35 milliliters of our HNO2. The titration is used with the same base with the same concentration, and then that methyl orange ends up turning from red to yellow. So it goes from acidic to then basic. The student claims that their indicator of choice is the best option, and then we have to agree or disagree and then justify. So then if we look back at the titration curve, we identified our range of the pH at equivalence as being somewhere from like 5 to like 11, but we really settled on 8. So then if we look at the pH range here, 3.1 to 4.4 is way too early for this to be a good indicator, that this titration has reached the equivalence point. So I would disagree for that reason, where the pH range for the methyl orange is too low. They don't ask for an alternative, but I mean, based on the given data, I would have selected the thymol blue because that's where we actually see the change in pH. The changes in color closer to the equivalence point compared to the methyl orange.